Here we go with some final example problems for discrete probability in Chapter 3. And today's bad pun is the Energizer Bunny has been arrested and charged with battery. Here we go. What are we going to cover? We're going to do 3 example problems that concern the application of discrete probability distributions. And this will help you identify the appropriate probability model. So we'll walk you through how to do these things. Some of the questions you want to be asking yourself: first, does the outcome of the random process involve one trial or a series of trials? If they're a series of trials, are they Bernoulli trials? In other words, we're going to focus on the aspect of Bernoulli where they're statistically independent. If they're statistically independent, Bernoulli lives. If not, Bernoulli dies. Does order matter for a given trial or between the trials? And lastly, how many outcomes are possible on a given trial? All of these factors will help us predict what probability distribution might be appropriate. They may not give you a 100% guarantee of finding the right distribution, but they'll sure help. So first, our first problem, let's cover an oil well. A company will drill 8 oil wells. Each one has 8% chance of successfully producing oil. Costs $15,000 to drill a well, and a successful well is worth $600,000. So what we want to know, first off, we want to know what are the number of trials? Well, 8. Is it Bernoulli? Are they independent? Absolutely. In the back of my mind, I often look at these kinds of problems and say, can I equate it somehow to some bizarre coin toss where each trial has a specific set rate of success and it has like an on-off, yes-no sort of thing? If it can do that, then probably binomial might be the best choice. And of course, order does not matter in this particular case. And lastly, number of outcomes on the trial, there's just 2. It's either successful or it's not successful. So let's go ahead and work this problem. It's binomial, obviously, binomial distribution, and we'll call S is the number of successful wells. Successful wells. And that's kind of like the X that we've talked about before, but we'll just call it S in this particular case. N is the number of trials, and of course it's 8 in this case. And P, probability of success, is 0.08. So if that's the case, we can go ahead and write out our equation. Probability that we've got 2 successes is just going to be n factorial over, well, I'll go ahead and I'm going to use S, but if I wanted to use X there, I could do that just as well. S factorial over n minus S factorial, probability S raised to the S, and 1 minus P to the n minus S. And in this case, it's going to be 8 factorial all over 2 factorial times 8 minus 2 factorial, and then multiply that times 0.08 squared, and then times 1 minus 0.08, that's our Q, and raised to the 8 minus 2 power, and all of that becomes 0.11. So that's the probability that 2 of the 8 wells is successful. Now for the second part, what is the company's expected profit loss from those 8 wells? This part right here, when you first look at it, you often just don't know how to do it. Then when I explain it to you, it's so easy that you don't know how you couldn't see it before. But I want you to really pay attention to it, because this is the kind of thing where it's so easy that you ignore it after you see how to do it, but then if I show it to you on a test, you forget how to do it again. So I don't want you to do that. So profit, loss, essentially you can calculate that. It's the expected value. Well, we can say it's 600,000 times however many successes we have, minus the costs, how much it costs us to drill each of those 8 wells. Okay, now look at there's our expected value. We can actually move that expected value in. We can say it's 600,000 times the expected value of S minus 8 times 15,000. What is the expected value of the successes? It's actually going to be just the mean, which for binomial we can calculate as n times p minus, and then this turns out to be 120,000. And when you calculate that all out, it turns out to be $264, which is a profit. Very nice, especially if you own shares in the company. So that's how you would approach this particular problem. Now let's look at a second problem. In this one, a company is considering buying a CNC milling machine. The average time between failures is 22.4 hours. You may not realize it, but that is actually a trick that I'm trying to play on you. What I want you to notice, whenever you have e2 raised to some power, whatever this is up here, it must be dimensionless. So if you've got an x up there, it better not be x pounds or x whatever. It's got to be dimensionless. So if you have something like e to the minus lambda t, between those two numbers, they must multiply out to cancel any kind of dimensions that you have. So if t is in units of time, which I presume it is, then lambda had better darn well be in units of 1 over time. So between the two of them, they cancel. So if I tell you that you've got an average time between failures of 22.4 hours, that is telling you it's 22.4 hours per failure. Now watch, if you put this up into e lambda t, well, wait a minute. If we say, and this is wrong, if we wrong, so I'm want to say wrong. But if we did say that, if we stuck that 22.4 into the same time hours per failure, and then put in t here and try to look at, we'd suddenly have some kind of bizarre units that's like hours squared per failure or something. So what this is really telling you is you must invert this. I love to give these kinds of inversion problems on tests, so just make sure you note it, and then it'll be like totally simple. So what you're actually given here is, in some sense, you need to deduce the real lambda, and that is 1 over 22.4 failures per hour, and that is 0.045 failures per hour. So that's the real lambda that you need to deal with. As far as t goes, let's see, it says the average time between failures remains constant. Darn good thing, otherwise we couldn't use the distribution we're going to use, and the actual time between failures is not dependent on when the previous failure occurred. So that's really telling you Poisson. So determine the probability that the machine will fail less than 2 times during 1 week's production, which is 5 8-hour days. So essentially we're saying that our t is equal to 5 times 8, which is 40 hours. Now I probably should go through, let's ask our little questions here. So number of trials in Bernoulli, well, we've got 1 trial, And Bernoulli isn't really even applicable in this particular Poisson process. So does order matter? Not a bit. And number of outcomes per trial? Well, infinite, because we could have an infinite number of failures. But this is quite clearly a Poisson type process. We'll, if we take a look, we can say that if it's a Poisson, then the probability of failure is going to be lambda t raised to the f e to the minus lambda t all over f factorial, or I could put that however I wanted to. I could put it as x. And then I can say the probability that the number of failures is less than 2 is actually going to be the probability that we'll have no failures plus the probability that we'll have one failure. Look at how this is something that people often miss, that we could have 0 failures or 1 failure. They get the 1 failure, but they forget that there could be no failures. So just don't overlook that. Then we can just plug into our formula. We'll say E is equal to, and I'm just plugging into this formula right up here, 0.045, right? And that came for what I had erased quite nicely earlier, but that's actually lambda times t, or that's actually lambda, sorry, and our t is 40, and we'll raise that to the 0 power, e to the minus 0.045 times 40, and put that all under 0 factorial, plus 0.045 times 40 raised to the 1, e to the minus 0.045 times 40, and put that on times 40, and then put all of this under 1 factorial, or over 1 factorial, and that becomes 0.165 plus 0.298, and that's 0.463, and that is the probability that the machine will fail less than 2 times during 1 week's production, given the parameters we've been shown right here. So on to our next problem, and this has to do with cards. I just want to go over quickly some calculations because I think these will help you understand how to look at the hypergeometric. First, what is the probability of choosing 5 cards, count them 5, from a deck of cards and having all 5 turn out to be hearts? Well, this is hypergeometric. Once we choose cards, remember, it does make a difference in the odds of what is remaining. So we'll just write down hypergeometric. It's going to be 13. All 5, the probability that all 5 would turn out to be hearts. Well, there's 13 possible hearts, and we're going to choose 5. What's that probability out of all the possible combinations? That's 52, choose 5. This is going to be 1,287 all over 2,598,960, and that turns out to be 0.000495, which is about 0.05%. So now let's see if we had, what's the probability choosing, oops, I should have moved that up a little bit, but anyway, what's the probability of choosing 5 cards from a deck of cards and having 3 turn out to be hearts? Well, that's 13, choose 3. Now, what's left? 39 left, and the other 2, we're choosing 2. And then that's based out of the entire flock of cards. So 52, choose 5. And that turns out to be 286 times 741, which is altogether over this 2 million number. 60, and that's 0.08 0.15, which is about 8%. That's a lot better. So you might ask, well, we'll buy that, but how come you didn't do that up here? I kind of did. Look, this I could put in 39. Let's see, I'm putting in a dotted 39. Choose 0, right? That's the remainder of those things. I could put that in there, but it's the same as 1, so I didn't bother to put it there. But it is sort of still there. So if you're looking for a good formula, it's always choose whatever you're choosing plus choosing whatever's left over. And that's what this is showing right here. So now, what's the probability of choosing 5 cards from a deck of cards and having 3 turn out to be spades or hearts, 1 a spade, and 1 be a diamond? Well, remember, we've got to put up here all of our choices, whether or not it's shown in here. So we know we're going to have 13, choose 3. That's for the 3 hearts. 13, choose 1 for the spade. And 13, choose 1 for the diamond. All over 52, choose 5. So that turns out to be 286 times 13 times 13. All over this $2 million, or 2 million, I wish. 2598,960, and all of that turns out to be 0.00559, which is approximately 0.6%, so smaller. So I think looking at cards like this really clarifies what's going on with having these types of combinatorials and how they fall out, and that will help us on the next problem. So just a reminder again, hypergeometric distribution. We're looking at n is the number of elements in the sample set, k is the number of events A. So that would be, for example, we've got 13 spades out of the 52 altogether, and x would be the number of times that an event is. And so then again here, the probability, this is just bringing this all back to mind, of hypergeometric. We've got some x, and we're choosing, oh, and we have n, little n, k, and we write this like k choose x, and then whatever's left over is n minus k over n minus x, and that's over n, choose n, and this is for 0 is less than or equal to x is less than or equal to n, and it's 0 elsewhere. So, oh, I actually have it right there. Okay, sorry about that. And here we go. We've got a batch of 33 parts containing 4 that are defective. The parts are randomly selected one at a time and checked for defects. Determine the probability that the 4th defective part is identified on the 10th sample. So the way we're going to approach this is let's put everything together. We'll first, for the probability that our defective part number 4 occurs on trial 10. So that is actually, if you go back to our definition of negative binomial, that is a probability that we'll have 3 defective parts in 9 trials union or intersecting with that given we've got 3 defective parts in 9 trials, we will have trial 10 is a defective part. So this is actually, since we're intersecting, it's the probability that we'll have 3 defectives in 9 trials times the probability that trial 10 is a defect, given that we've gotten 3 defectives in 9 trials. So this part right here is going to be the hypergeometric. I think that's pretty clear from what we've just been doing. And in this case, n is going to be 33, k is equal to 4, n is equal to 9, and x is equal to 3. So let's write this all out. The probability that we'll have fourth defect on trial 10 is just, and here's our hypergeometric, and that is, I'm going to write down the, let's see, kx, the combinatorial of kx, and then the combinatorial of what's left over, which is n minus k, n minus x, and then over that combinatorial of n and little n. And then, well, what's this last probability? That is, given we've had 3 defectives already in 9 trials, that on the 10th we'll have a defect. Well, let's see. If we've had 3 defects already in 9 trials, essentially what we're saying is we've got 33 minus 9. Well, we've got 1 chance in 33 minus 9. So that's actually 1 in 24. So let's write this all out. Let's say 4. This combinatorial turns out to be 4. And this one is 475, 0, 2, 0, over 38,567,010 times 1 over 24, and all of that turns out to be 0.49. So we went below even the negative binomial, and we went right back to first principles. But if you do the negative binomial, you will get exactly the same result. Oh, and here, I should have done this. Sorry, forgot about this. But number of trials in Bernoulli, it's 10 trials. They're not statistically independent. Does order matter? Only for the 10th part, of course. And number of trials, outcomes per trial is 2. So let's move on. It is now 1941, and we're talking about the Germans bombing Moscow. Most people in Moscow, quite intelligently, flee to the underground bomb shelters at night, except for a famous Russian statistician who tells a friend he's going to sleep in his own bed, saying, "There's only one of me among 5 million other people in Moscow. What are the chances I'll get hit?" He survives the first night, but the next evening he shows up at the shelter. His friend asks him why he changed his mind. "Well," says the statistician, "there are 5 million people in this city and 1 elephant in the Moscow Zoo. And last night they got the elephant." And here we go. Okay, so with that, we'll go on to the next problem, which involves 2 vacancies in a certain statistics department in Sequim, Washington. Now, you may wonder that, yes, Sequim is pronounced squim to rhyme with swim, and it is located right around here. That's where Sequim is. And we've got 5 individuals applying for a position there. 2 have expertise in linear models. 1 has expertise in applied probability, and the search committee is instructed to choose 2 members randomly. What's the probability that the 2 chosen are those who have expertise in linear models? And what's the probability that from the 2 chosen, 1 has expertise in linear and the other in applied probability? So here we go. What you might miss right off the bat is we've got people with expertise. We've got, out of the 5, 2 with expertise in linear models, 1 with expertise in applied probability, and 2 other. So we've actually got 3 different possibilities here. So this means general hypergeometric is our way to go. So what's the probability that 2 chosen are those with expertise in linear models? What we're really looking for here is the probability that, and remember our K is, we've got 2 with expertise in linear models. So that's our K, that's our maximum value right there. We're saying 2, and we're going to write this out just so we can see. It's 3 choose 0, which turns out to be 1, but we knew that. And out of the total number of combinations, which is 5, choose 2. If we work that out, it is 0.1. So that's the probability that the 2 chosen are those with the expertise in linear models. Now for part B, what's the probability that from the 2 chosen, 1 has expertise in linear and the other in applied probability. So in that case, we're looking for, well, the linear has 2 and we're choosing 1, and we're taking 1, choose 1, and so that's our total choice right there. And this is 5, choose 2 again, and we'll take that 0.2. So there we go. It's just 20%. Let's try another problem. We've got a couple who decides they're going to continue to have children until they have 2 little munchkin boys. So assuming that the probability of a male is 50%, which it actually isn't. It's a little higher than that. It's something like, I don't know, 0.52. What is the and that was actually at the heart of many statistical debates over centuries. But what is the probability that their second male child is, or their second male is their 4th child? Well, I think it's pretty clear from this that we're going to have negative binomial distribution. And just to bring that back to mind, that's a distribution of this form, x minus k, or x minus 1 over k minus 1 to the pk times q x minus k. And plugging in our numbers here, we can say, well, x is 4 minus 1, and k is going to be 2 minus 1. And then, well, we're saying it's 50/50 squared. And again, over 0.5 and squared. And if you work that out, it's 0.1875. Check. So not too bad. So let's go to the next problem. And that involves a note on observation methods. It turns out that the probability of someone watching you is proportional to the stupidity of your action. Ha! Okay, so now we're going to go on to talk about intersections. And this one gives us a good way of using the Poisson distribution. And just to make our life easier, I've drawn it up right there. There's our Poisson. Now this particular problem involves time. I have not tried to trick you in this problem. I haven't inverted the lambda. It actually is in traffic accidents per month. So lambda is equal to 3 accidents per month. Or we can just say 3. And then we can now say that if we plug in our numbers, what's the probability of 5, exactly 5 accidents occurring? It's just going to be 3. I'm plugging into this thing right here, right? 3 times RT5 in any given month, so it's 1 month, and then raised to the 5th, and then e to the minus 3 times 1 all over 5 factorial. And when you calculate that all out, and that's 0.1008. So that is the first one. Now, less than 3 accidents will occur. Well, that's going to be the probability of 0 plus probability of 1 plus the probability of 2. So I'll write this out here. 3 times 1 raised to the 0 power all over 0 factorial e to the minus 3 times 1. One thing to notice is, what if I said instead of any given month, I said for a 2-month period or a 3-month period? Then you'd be plugging in t is equal to 2 or 3 wherever t appears right here. So at any rate, plus 3 times 1 raised to the 1 power e to the minus 3 times 1 over 1 factorial, and 3 times 1 to e to the minus 3 times 1 all over 2 factorial, and all of that turns out to be, if you add it all up, is 0.4232. Now this was A, this is B, and C. At least 2 accidents will occur, at least. So that means it's going to be the probability that x is greater than or equal to 2, which is 1 minus the probability that x is less than or equal to 1. And you may guess then it's going to be 1 minus probability of 0 and then minus probability of 1. And you can see what 0 is and what 1 is up here. And when you calculate everything out, it should be 0.8009. Okay, so that's what we've got right there. Now let's move on to the next one. And this one involves heart failure. So we've got heart failure that's due to either natural occurrences, 87%, or outside factors, 13%. So we've basically got two choices, heads or tails in some sense, with a little bit different odds than 50-50, but this is kind of a heads or tails sort of condition, and all the rest of this verbiage here just amplifies on outside factors and so forth. We've got 20 patients that visit an emergency room with heart failure, and the causes of heart failure are independent. Bernoulli lives. This is clearly something that's akin to a coin toss situation. So we're going to use the binomial. What's the probability that 3 individuals have conditions caused by outside factors? Well, we can say that our n is equal to 20, and our probability of success, so to speak, outside factors, is 0.13. So we'll say for part A, probability that x is equal to 3 is just 20, choose 3, times 0.13 raised to the third, and then 1 minus 0.13 raised to the 17th. And when you calculate that all out, it's 0.235. So what about part B? The probability that 3 or more individuals have conditions caused by outside factors. Well, here we're saying that in essence it's the probability that x is greater than or equal to 3, which is equal to 1 minus the probability that x is less than or equal to 3. And so that would be 1 minus probability that x is 0, probability that x is 1, and probability that x is 2. And I think you can do the plugging and the chugging in there. Your solution should be 0.492. Now for C, what are the mean and standard deviation of the number of individuals with conditions caused by outside factors? Well, we'll just take the mean is expected value is n times p, 20 times 0.13, and that's just 2.6. And the variance is np, as 1 minus p, is 2.262. So the standard deviation will be the square root of that, and that will be 1.504. So check. Let's look at one more problem. I like this problem because it's a Poisson, clearly, but instead of using time, we're using space. And this Poisson distribution, it can be very useful for spatial types of problems as well. So we'll see that right here. Okay, now the trick on this problem is use the technique I'm showing you here. Plug it into this equation, because then you won't mess up. The way the book currently has it, at least, and they're supposed to correct it, it can make it more difficult to do these kinds of problems. So let's go for A. What's the probability there are 2 flaws in 1 square meter of cloth? I'm just going to plug into this equation. Probability there's 2. Our lambda, we're clearly told right up here, is 0.1 flaws per square meter. So we'll say 0.1, and y is 1 square meter. So it's 1 times 1. and x is 2 e to the minus 0.1 times 1, and we'll take all of that to the 2 factorial. Okay, so we plugged it all in. When we work it out, it will be 0.0045. Now for B, what's the probability there's one flaw in 10 square yards of cloth? So we're looking probability of one flaw in 10 square yards. So we're going to say, now we're going to say lambda 0.1 again, but now it's multiplied by 10, and now our x is 1, and e to the 0.1 times 10, and all of this is over x factorial, and x is 1 factorial. So that should turn out to be 0.3679. So you can see there's a lot more cloth, a lot more probability of this happening. Oops, I forgot the minus sign right there. Otherwise it would be blowing up. We don't want that. Okay, so now we'll say, what's the probability that there are no flaws in 20 square yards of cloth? So probability, there's no, and we're going to say 0.1, 20 raised to the 0 power, sorry that's kind of overlapping there, e to the minus 0.1 times 20, and we've got 0 factorial, and that all ends up being 0.1353. And actually this is D right there. So now we've got probability of D. What's the probability there are at least 2 flaws in 10 square meters of cloth? So I think you see where this is going. So we're like just doing all sorts of, we've got 10 square meters, and now it's e to the minus, oh, and that was 2 flaws, so we're raising it to the 2 power, e to the 0.1 times 10, and all of that over 2 factorial, and then when we multiply it all out, 0, well, wait a minute, probability, oh, wait a minute, it almost tricked me. There are at least 2 flaws, not 2 flaws, but at least 2 flaws. So this means 2 or greater. So look at that error that I made there. Ha! We've actually already calculated out what we needed to know. So it's good that you saw me make that error and that you saw me correct it. So error. Do not do this in quizzes. Since it's at least 2 flaws, what we really want is the probability 1 minus the probability that there's 0 flaws minus the probability that there's 1 flaw. That will give us the probability that there are at least 2 flaws in what we're seeing. So, oops, sorry about that. We should say greater than or equal to. Okay, so when you calculate, and I think you can see we've already done it enough. All you have to do is plug in for 10, and then you've got to plug in for 0 flaws. You've got 10 square meters and 1 flaw, and then subtract off the both of those. And when you do that, you should get 1 minus e to the minus 1 minus e to the minus 1, turns out to be this time, and that is 0.2642. So there we go. And finally, we must remember about statisticians. Did you hear the one about the statistician who had his head in an oven and his feet in a bucket of ice? When asked how he felt, he replied, "On average, I feel just fine."